Hey, good afternoon. In today's video, what we're going to be doing is discussing three interacting tanks as a way to understand the concept of dynamic material balances, which is simply the accumulation deals with the flow rate of something going in minus the flow rate going out minus what's consumed. And so we're going to be dealing with three interacting tanks to help understand that concept. And then in this video particularly, we're going to want to derive the differential equations of the fluid levels per tank. And so we're going to want to be able to understand what is the fluid level and the flow rate for the fluids per tank with respect to time. And so to go ahead and dive into that, one of the concepts to start with is this concept of interacting tanks. And so we can see here that the flow rates are all at the bottom of the tank there, meaning that it's not like one is pouring into two being down here and then tank two is pouring into tank three and therefore the tanks are independent of each other. Here they're actually interacting with each other, and so the height of the fluid levels in each tank is going to matter. And so if, for example, the height in tank one was higher than the height in tank two, then the flow rate would be going from tank one into tank two. If vice versa, the height of the fluid level is higher in tank two, which here it is initially in our initial parameters, then in tank one, then the flow rate is going to go from tank two into tank one. And so that's the way that the flow rates are interacting with each other depending on the height of the fluid levels. And so here are our initial parameters before we dive into the specifics of how we're going to derive the differential equations. So our cross-sectional area for tank 1 is 0.5 meters squared. Then for tank 2 we have 1 meter squared, tank 3 2 meters squared. Our proportional control, which is going to be how we dictate the flow rate coming in to tank 2, is going to be 0.1 meters cubed per second. Then our flow rate coming in, which is going to be flowing into tank 2 here, is going to be our proportional control, and we're going to have a set point for, and we're going to use tank 3, we're going to give a set point for tank 3 and minus the actual fluid height at any point in tank 3 multiplied by the proportion control. Our set point is going to be 4 meters, and then our proportionality constant is going to be for all three tanks, 1, 2, and 3 is going to be 0.1 meters cubed per second. And then our initial heights for each of the fluid levels is 0.5, 1, and 2 meters for each tank there. Let's go ahead and talk about now how we're going to understand the rate of flow from each of the tanks. So we've got what's going to be flowing in. Now we have to also understand what's going to be flowing out of each tank and how to do that. And so let's go ahead and get that going here. An important equation that is going to help us understand this is Bernoulli's equation. And so here we've got the proportionality constant multiplied by the absolute difference between the heights. So in this case, we'll say height, just n in particular, minus height m, and the square root of that. And so that is going to be what dictates the flow rate out of the tank. Now, with regards to tank 1, we've got our what's coming out from tank 1 to 2, and then what's coming out, flowing out from tank 2 is going to be from 2 to 3, and then lastly, what is flowing out from tank 3 is just flowing out from tank 3. So first off, dealing with tank 1, let's go ahead and start with tank 1 here. And we have that our flow rate from tank 1 to tank 2 is going to be the proportionality constant from 1 to 2, and then the difference between the height of tank 1 minus the height in tank 2, and that to the square root, or to the 1/2 power. And then let's pause for a second, because if we just leave it at this and we end up having the absolute value, it's not going to end up showing the direction of the flow, either to the left or to the right. And so we have to be able to have a way to designate that. And so what we're going to be able to do here for that is add in the sign between H1, the fluid level, in tank 1, minus the fluid level in tank 2, and then this multiplied by the proportionality constant of the difference between the heights between tank 1 and tank 2. What is going on with sign? What are we doing with that? What happens there is, if any negative value happens, it just ends up multiplying. This becomes -1, and so it multiplies all of this by -1. And then if this happens to be positive, regardless of the positive value, this becomes just +1 multiplied by all of this. So then in this case, any negative numbers would be flowing from tank 2 into tank 1. Any positive values would be flowing from tank 1 into tank 2, and that will be how we're able to differentiate which direction the flow rate is going for the fluids. So that is for tank 1. Now tank 2. Now for the flow rate from tank 2 into tank 3, we're going to do the same concept here, which is flow rate from tank 2 into tank 3. It's going to be proportionality constant between tank 2 to tank 3. And this is going to be the height difference of the fluid height at any point from between tank 2 and tank 3. And again, we need to dictate the flow, the direction of flow rates. So all we're doing here is the same concept, just dealing with tanks 2 and 3 here. I apologize, the software I'm using, it lags with the writing, and so then it gets choppy and it doesn't actually catch some of the writing there. There we go. Okay. So this is dictating our flow rates from 1 to 2, and then from 2 to 3, and then from 3 out is just going to be our whatever's flowing out from tank 3. Let's go ahead now and actually express this in terms of our differential equations. So for tank 1, we're wanting to know, and for each of the tanks, what is the rate of flow, what is the rate of volume with respect to time per tank. And so volume is simply the cross-sectional area of the tank multiplied by the height. So volume is the area times the height. Well, we're wanting to know, in this case, the area of the tank isn't changing. It's a constant, right? The tank's not like morphing in different shapes and sizes. And so the thing that is changing, though, is the fluid level within the tank with respect to time. And so we're going to go ahead and express that here, which is our fluid level height with respect to time. And what does that equal? Well, that is going to equal, let's go ahead and take a look over here, anything that is leaving, this case here, it equals what's leaving tank 1. So that's going to be our change of flow. And so that's going to be negative flow rate from, go ahead and write just to specify. everything flowing out of tank 1. Now, for tank 2, it's the same concept, the rate of volume with respect to time. And again, of course, the cross-sectional area is a constant, but it is the fluid height in tank 2 that's going to be changing with respect to time. Now, let's see what needs to go into this equation for us. Well, we have to consider the various factors here. So we have to consider that we have what's coming into tank 2. We have to consider what's coming into tank 2 from tank 1, so what's coming into tank 2 just from outside sources, what's coming into tank 2 from tank 1, and what's leaving tank 2 into tank 3. And so here we've got what is flowing in to tank 2, what is being added to tank 2 from tank 1, and then what is leaving tank 2 into tank 3. And then lastly, it's going to be tank 3. In this case, for tank 3, again, we have our rate of volume with respect to time. And here we've got what's being added in from tank 2, and then what's going to be leaving tank 3 altogether. Now, when we're going to be dealing with the fluid height with respect to time and as an isolated component, we're going to have to divide our flow rates in and out of the tanks by the cross-sectional area. And so we'll go ahead and also express that here. So this is going to be divided by the cross-sectional area of tank 1. This is going to be what's flowing in to tank 2 and what's leaving tank 2. All of this divided by the cross-sectional area of tank 2. And then lastly, for tank 3, it's flowing into tank 3 from tank 2, and what's leaving tank 3 altogether, divided by the cross-sectional area of tank 3. And so this is expressing our flow rates in and out of each of the tanks with respect to time with their differential equations derived here. And so in part 2 of this video series, what we're going to do is actually solve the dynamics happening when we use proportion control on tank 3 to help dictate what's flowing in and what's flowing out. And so before we move into video 2, there's just one last thing to unpack here, which is going to be the concept of the proportion control that we're going to be using in the next video. And so in this case, what we have going on here is our set point, which we've chosen to be tank 3. It could have been any of the tanks. We've just chosen to use it as tank 3 here. So let's talk about what is happening here with this proportion control. So we've set our set point for tank 3 to be 4 meters. What that means here is if this is higher than the actual fluid level in the tank, so if this is 4 and this is 3, then that's going to result in this being positive. And that's what we want, because if the actual fluid level in the tank is lower than the set point that we want it to be at, then we want fluid to be flowing into tank 3. And then vice versa. If the actual fluid level in tank 3 is higher than the set point that we want, well, then we don't want any more fluid. We want fluid to be leaving the tank, and so we want this flow rate or this proportion control to be negative, because we want to be pumping fluid out of tank 3 in order to get to our set point. And so it's kind of acting like a cruise control on your car. You set it you want it to be 60 miles an hour. You go up a hill, your car starts to slow down, and so your car adds some extra acceleration to get you back up to 60 miles an hour, and all of a sudden you go back down the hill, and now you're going too fast, you're going 65 miles an hour. You want to have the engine or the car slowing down, and then to be able to keep you at that steady 60 miles an hour. And so if it needs to speed up if it's going too slow, and slow down if it's going too fast. That's exactly what we're doing here, except with just fluid levels. And now, so in the next video, we're going to actually simulate and calculate the dynamics of everything that we've derived here in this first video. Thank you.